Right, well, hopefully this is the last time we'll have to do a recorded lesson, and I'll be back next lesson. First of all, just thinking about what you've done this week, I'd like you to spend 3 minutes, write the question, write the answer. Today's title, if you want one, Faith, is reversible. Reactions. And then whoever's covering will pause for 3 minutes and let you answer those 3 questions. Okay, so let's see if you got them right. How do we make reactions faster? Increase the temperature, increase concentration, increase the pressure on gases, large surface area for solids, and we could add a catalyst. Question 2, why does increasing concentration increase the rate of reaction? In a higher concentration there are more particles in the same volume, so there's a greater chance of collisions. And the last one, why would we even want reactions going quickly? Well, so we can make things faster. We can make chemicals, products, etc. faster, and therefore industry making more money, which is the point of industry. Okay, so what is a reversible reaction? Well, a reversible reaction is where the reactants can turn into the products, but the products can also react and turn back into what they originally were, the reactants. And that's what this symbol here means. So this symbol is the symbol to represent a reversible reaction. Now, whoever's covering will pause now, so you get a chance to record that bit and explain what reversible means. It means a reaction can go both directions at the same time. Okay, so hopefully you've got that in your notes. I gave enough time for a pause. The next thing with reversible reactions is energy. And if the reaction going forwards is exothermic, so this will be going back to chemistry 1, exothermic means it releases energy from the reaction. You'd know it as a reaction that gets hot or maybe gives out light, so that releases energy. Then the opposite, to go back the other way, it must be a reaction that takes in energy, endothermic, which takes in energy. So if one direction is exothermic, the other one must be endothermic, and vice versa. If I'd like this reaction to go forwards, if I'd like it to go this way, how could I encourage it to release energy? Well, actually, if I made it a bit cooler, it would give out more energy. You'll find it easier to give out energy. However, if I wanted it to go this way and it takes in energy, well, what I could do is make it warmer and I could give it more energy to encourage it that way. So I can try and control which way it's going, so that if I want it to make the products, I can go that way, and if I want it to make the reactants, I can go that way. Right, pause there. Add on the bit about the fact that in one direction these reversible reactions will be giving out energy, and in the other direction they will be taking in energy. And if that's something that's still not sticking for you, if that exo and endo is still not sticking for you, you might want to make a point of that and highlight it. Remember, X is out and N is in. And the way to remember it, you can have an entrance to a room where you go in, or you can have an exit from a room, which is where you go out. So as long as you remember in the hall that the exit and the entrance, then actually you'll remember that X is out and N is in. Right, pause there, record that stuff. Excellent, lovely jubbly. Hopefully you're all keeping up, including 5 people whose names were sent to me by Mr. Stubbs the other day. Now this is one you have to know. Copper sulfate, and we'll look at this in class. Copper sulfate is blue. No, it's not. Copper sulfate is white. How can it be blue and white? Well, what happens is when it gets damp, when it joins up with water particles from the air, it's blue. When it's heated and it loses the water, that water escapes off into the air, then it's white. And that's an example of a reversible reaction that you need to know. So this hydrated, get my pen in the right place as always, this hydrated copper sulfate that is blue takes in energy when you heat it, because here is the endo in heat, in energy. If I heat it, it goes this way and it produces white copper sulfate. If I then just leave that white copper sulfate for a few hours, it will take water back from the air, it will get warm itself and give out some heat, and it will turn back to blue. So when we order this from the prep room, it always comes as blue because it's been sat around for a while in there, it's blue. If we want to get the white one, the anhydrous copper sulfate, we'd have to heat it. So again, if I make it hotter, I can encourage the forwards reaction. That one. Sorry. And if I make it cooler, I was right, I can encourage the backwards reaction. So how can we use this? The next thing is this word here, equilibrium. And what does that mean? Well, when we start off here, number 1, this diagram, you're going to be drawing these diagrams in a minute. Look at all those coloured dots. Wow, how exciting to draw this with all your different highlighters. You're going to have such fun. I can see your little faces now thinking, wow, this will be such fun. Yep, you are thinking that, brilliant. So when we start off with A and B, our reactants, there is none of the other chemical there. So what happens here is that forwards reaction is nice and fast. Lots of collisions and the reaction happens. Reaction. The forwards reaction happens quickly. Forwards. As it starts to make some C and D, well, you've not only got this reaction going forwards, you've also got this reaction now starting to go backwards. But as I've drawn with the arrows here, it's not as big, so it's still going more forwards than backwards. However, it will reach a stage when this reaction, forwards, and that's how you have to write about them. You write about the forwards and you write about the backwards reaction. It will reach a stage, backwards. It will reach a stage where the forwards reaction and the backwards reaction are going exactly the same speed, the same rate. Same rate. So at that stage, it will no longer look like it's changing, because every time A and B join to make C and D, well, C and D are joining to make some A and B. So when the two have reached exactly the same rate, and this is the important bit over here at the very end of your diagrams, then it will have reached a point where we say, it has reached an equilibrium. So we're going to pause. You're going to do lots of little diagrams really neatly with pencils and rulers and lots of little coloured dots, so it's really clear in your notes. And then you're going to explain stage 1 over here, where just the forwards reaction starts with A and B. 2, both reactions are now happening but not at the same speed. And 3, both reactions are happening but exactly the same speed now. So it doesn't look like it's changed, so it's reached equilibrium. Right, pause and draw and write. Okay, now this is a reaction to do with nitrogen in the air, which is a G, gas, and hydrogen, which is a gas, making ammonia, gas. And this process was named after this little man over here, whose name was Fritz Haber, or Haber, whichever one you like, because you only have to write it, you don't have to be able to pronounce it. Now the Haber process is this reaction. What they worked out with this reaction was, it was, let me get this right, it was exothermic going forward and endothermic going backwards. So ideally, to make lots and lots of ammonia, which ammonia is used to make fertilizers. Now, I know what some of you will think of fertilizers. Fertilizers give essential nitrates to plants. So as the world's population has gone up and up and up, it's even more important that farmers have lots of fertilizer to put the nitrates into the soil to help plants grow. So therefore there's enough food for all the people. So this is one of the most used reactions in the entire whole world, always. Now, what I wanted to sort of go on to on this page, once you've recorded the fact that we need ammonia for fertilizers, this is a really useful reaction, etc. What I wanted to go on to was the fact that here, to help this exothermic reaction make more ammonia, here, I really want it to be cold. But what we learned earlier in the week, so cold would give us a high amount of ammonia. Now, I would think some of you, and a lot of you are quite clever scientists, some of you are thinking, hold on, high temperature is better for reactions because we learned that on Tuesday or Wednesday, or Thursday. A high temperature gives us a very fast reaction. So what do we do? Do we go for a cold reaction, which gives us lots of ammonia, but we only get it slowly, or do we go for a high temperature that gives us a little bit, but it gives us incredibly fast? And the answer is we don't go for the cold. We deliberately go for a little bit quickly. We go for this one, and actually that process is done at 450 degrees Celsius. So sometimes what you're asked to do is you're asked to explain why have they used a high temperature, and what you'd say is, for example, well, a high temperature doesn't help us make more ammonia, but it does help us with a really fast reaction. So we've done a compromise. Right, that's going to take you a little while to record. And you've probably paused and recorded now, I hope. And then we've got this one. Now I'm going to go past this and go over this in class for now. But with the Haber process, what we're doing here is, I'm going to try and choose a highlighter that is a different colour. Hey, nice green one. Here, as the reaction starts, you have to put in this much energy for it to react when they collide. Then you get this much energy out. So we know we get more energy out here than we put in. So this is an exothermic reaction. I'm just writing exo at the moment because I'm lazy. Now, with the Haber process, I'll change highlighter again. If we could add a catalyst, we could decrease the amount of energy needed. And the catalyst we use for the Haber process is iron. So remember, the catalyst doesn't take part in the reaction, but when we do that adding nitrogen and hydrogen gas together to make ammonia, we do it in the presence of iron, and just by iron being there, it means the particles of nitrogen and hydrogen don't need so much energy. Right, done that. Dynamic equilibrium. Right, now this is a bit of a, for most of you, absolutely easy as anything. Equilibrium, when things are equal, they are the same. And we just explained a minute ago, why are they the same? Well, they're the same because the reaction forwards and the reaction backwards are going at the same rate. So it looks like the reaction is not changing. So what does the word dynamic mean? And I thought this was fairly easy, and I discussed it recently with some students, and they came up with all sorts of answers. But the word dynamic, if you had a dynamic personality or you were a dynamic person, dynamic actually means really active. So what this means is the reaction is actively staying the same, because every time the forward reaction happens, the backward reaction happens. So it looks like nothing's changing, but it's very, very actively staying exactly the same place. So it's just a little bit added on to the equilibrium bit. When you've done that, you can move on. And the only other thing to say about that dynamic equilibrium is it needs to be in a closed system. By a closed system, we mean that no chemicals can, nothing is added to it during it, and nothing is lost from it. So here, for example, over here, you've got a reaction happening inside a conical flask with a bung in the top. It's closed. Nothing else can be added to that. Here, for example, putting these under pressure, it's inside a container where nothing can escape from it. But a closed system just means that the reaction is happening inside a container, inside a reaction vessel, something that things aren't added or lost from. And we've already done this, and we've already done this. So when we reach this point, and we reach a point called equilibrium, that's great. The reactions are happening the same rate, but what happens if I want it to shift to the other side? And just go over the same thing again quickly. The reaction forward is exothermic, the reaction backward is endothermic. If I do this reaction at 20 degrees C, then maybe what I end up with is I end up with 50% of it, half of it ends up as nitrogen and hydrogen, and 50% ends up as ammonia. If I then make it colder, if I do it at 5 degrees C, I'm encouraging this one, the top reaction. So maybe then what I get is 40% left here and 60% here. So all I wanted you for the very end of this lesson is, with the equilibrium, just draw an arrow to it, with the equilibrium, we can shift it. We can change the equilibrium by changing the reaction conditions. Okay, right, I'm going to stop there.